Welcome everyone to Science is Cool. Yeah, Science is Cool in the Hawaiian Islands. We're in Hilo, the big island of Hawaii, and we're guests of Imaloa, which is an amazing visitor center part of University of Hawaii. And we have a, everybody's been great. We've been having a great day today. I see Ning Lee is on, Olivia Hughes. Great to see you guys. Okay, well, Olivia and Ning, I just want to you're both with PacIOOS, right? And we're
Yes.
going to talk about wave buoys and waves. And I can't wait for this. This is really interesting. We've had an amazing day, and I don't know if you've seen any of it, but we're just
Uh-huh.
having a great time here. So, what I'm going to do is we don't have any housekeeping. I'm just going to let you guys go, and I'll be watching the chat. We've been getting a lot of questions. So at 2 o'clock, we're going to hit the Q&A. I'll pop back on for you guys, and the audience is super engaged. You're going to get a ton of questions, and I will just let you do your thing there. And I can't wait to talk to you again. And see you in 20 minutes.
That's great, Dave. Thank you for having us. I will start first. My name is Ning Li. My background is coastal engineering, and I am a numerical wave modeler with PacIOOS to provide the operational wave forecast for Hawaii, for American Samoa, for Guam, CNMI, and also Palau. So how about you, Olivia?
Thank you so much, Ning. Yeah, so my name is Olivia Hughes, and I got started at the PacIOOS Wave Buoy Lab when I was a freshman environmental science student at UH Manoa. And after graduation, I became a full-time technician for the Wave Buoy team. And since then, I've been climbing the ladder, and I'm now considered a Wave Buoy specialist at the PacIOOS Wave Buoy Lab.
Wow, that's great. So yesterday, probably some of you attended the tsunami section, and today we are going to talk about a different type of waves, which is the wave we commonly see at the beach. They were generated by wind. But why today we talk about this wind-generated waves? First of all, because it's very important for our daily life for the recreational purpose, like a lot of people probably surfing with those beautiful swells. And also it also very important for regulate the global climate and also help with the coastal ecosystem. However, when waves became too big, it can also put risk to the marine traffic and also cause coastal flooding and the erosions. We have two um, uh, photos about so you can see these photos. It is a house almost fall into the ocean in 2022, and then we have another one for 2024. This is the real life, like when the waves interact with beach, it can cause erosion and cause a lot of damage. We also have a short video that you can use to demonstrate the effect of waves on the beach. As you can see, as waves keep coming to the beach, it breaks and also gradually eat up those sand in the beach and cause erosion. As the sand gradually loses into the ocean, it weakens the foundation, and after a while, then the house falls into the ocean. This is like a very easy kit you can easily set up in your classroom to show your students the concept of erosion caused by waves. After millions of cycles, the effect can be devastating. After a while, at the end of this video, you can see the house by short. This is a Lego used to demonstrate the house, and after a few cycles, the house will fall into the ocean. So since waves are so important for our daily life, so for those who live in the island, inside of the island, you probably start your day by looking at the weather forecast. For us, we live close to beach, close to ocean. Not only we look at the weather forecast, we also look at the surf forecast. We have a forecast video that's just very common for is very important part of everyday life. Scott, I think you can play the.
Aloha on this
Yes.
Wednesday. We're looking at another nice breezy day today. We're going to start out with a few showers, mainly for a handful of windward and Mauka spots. Not a lot of rain because the rain will be moving through rather quickly because of the breezy winds. It's going to be a windy day again today. Very pleasant conditions with lots of afternoon sunshine. High temperature running to about 87 degrees. That south swell is still hanging on. We still have some fun-sized waves on the south shore, but heads up, box jellyfish likely swimming in. And east shores remain rough and choppy.
Great. So you can see from this surf forecast, it talks about how high the surfing is, and then, but where does the information of the surf forecast come from? So part of the data is from the Buoy data and also the model data me and Olivia, we have been working with. So before we jump into the wave data, do you know where the surfing, the swells come from? For those we live in Hawaii, we all experience beautiful surfs. And then we have another little video with a wave tank shows how waves are generated. You can see as the wind keeps blowing on the water surface, the energy from the wind transfer into the water, and the waves serve as the interface between the air and the water, like between the air and the ocean, and it generates waves. As the wind keeps blowing, the wave grows bigger and bigger. As it grows, it also travels. So at the beginning, it's a little bit chaotic, and after a while, the longer period the wave travel faster, and the shorter period wave travel slower, and they disperse. That's why when we have a weather system far away, and few days later, we have beautiful swells people can surf with. And we have animation of the weather. It's from the windy. This is the weather forecast. You can see around Alaska, there is a weather system. We call it the extratropical cyclone. The purple color means strong wind keep blowing over the North Pacific. And then as this strong wind blowing, large waves get generated. And a few days later in Hawaii, we get beautiful swells at the North Shore. So now we know in the middle of the Pacific, the waves will originate from Alaska. It's the warm, beautiful ocean. The water also come from Alaska. That's probably a question your students may ask you. So we have a little demo to show the students that as wave travels, it only carry either the movement or energy. It actually does not carry the water mass. You can see with this little kit, as we use the handle to generate waves, on the surface, it will go up and down, and it create waveforms. But under the surface, actually the water particle go circles. So as one wave pass by, it will go back to the original location. That's why our beautiful waters in Hawaii is not from Alaska. So then how do we define a wave? And there is 3 parameters we commonly use. One is wave height. It is the distance from the wave crest to the trough. Crest is the highest point, and the trough is the lowest point. And then the distance between them became wave height. And then wave period is you fix at a fixed location when it experiences two peak or two crest or two trough, then it's the time between those two is a wave period. And the wave length is a horizontal distance between trough to trough, crest to crest. It's very easy to measure on the paper, isn't it? But in the reality, in the ocean, how do we measure waves? That's what Olivia has been working. So Olivia?
Yeah, like Ning said, that is where I come in. Oh, that picture. Right away. So in the ocean, different labs have lots of different ways to measure waves. In the PacIOOS Wave Buoy Lab, we have two different types of instruments to measure waves. The first one is the wave rider buoy that you can see behind me. And as you might have observed from the picture or this picture behind me, it's quite large. It's about 3 feet tall, 3 feet wide, with all the bells and whistles attached. This weighs in at about 550 pounds. These wave buoys measure wave height, wave period, which, like Ning said, is the time it takes for one entire wavelength, crest to crest or trough to trough, to pass through the buoy point. It will measure sea surface temperature, and it will measure the direction that the waves are coming from. I think our newer models, they will also measure the direction that the wave current is coming from, like Wave demonstrated how the underwater, the waves were circling and churning like that. And it will the antennas will also measure air temperature directly above the water level. But how does it work? That is thanks to this guy right here. And forgive me, I'm going to have to stand up to show you exactly how it works. This is a very large gyroscope. This is a broken one that we use for demo purposes. And you'll notice there's a plate kind of in the center line right here. I'm doing my best to hold this up. It is quite heavy. And a wire that connects from the plate to the top of the ball right here. And the idea is no matter how hard the waves bounce the buoy up and down, no matter how hard they spin it or turn it over any which way, this plate is working as hard as it possibly can inside the saline solution, a little bit denser than water, to stay as still as possible. I have to set it back on its stand so I don't pass out trying to hold that thing. So as the plate's working hard to stay still, the wire is sending that data up to the top of the ball, and a computer is plugged in right here. Actually, Scott, do we have that picture of the diagram of how the buoy works so I can show where this gyroscope is inside the buoy? Perfect, yeah. So if you see this picture and that little canister at the bottom picture of the buoy, that's where this gyroscope sits. And directly on top of it, plugged into a computer, will be plugged into the gyroscope right here. And it's interpreting all of that data and turning it into quantitative wave data, which is how we get all the information about our wave parameters. And so that buoy will be collecting all that data every few seconds. I believe the ratio is like 2.45 seconds. And every 30 minutes, the computer will average out all that data it's gotten, send it up to the satellite, and the satellite sends it back to the PacIOOS Wave Observation site, which I believe is linked in the resources page, and also sends that to Ning so she can keep making wave forecasts around Hawaii. So my job, kind of like you saw in that picture earlier, is that to make sure that all of the buoys at these stations around Hawaii and American Samoa and Saipan and Guam stay in the ocean at their locations as long as possible. So I get all the buoys ready, I replace their batteries, I get them all shined up and pretty, I build their moorings, I put together their anchors, I get in touch with the local fishermen or anyone else who has a boat big enough to take my team and I and all of our equipment out into the ocean wherever we want to drop the anchor and push it in the water. And ideally, we'll have these buoys collecting data for up to 3 to 4 years, depending on how long the batteries last, until they're out of battery. And I have to go and get them and bring them back to the lab and start the process all over again. Sometimes, however, I'm not as lucky. And Scott, I believe I have another picture for this part. Sometimes buoys come loose. Sometimes they're separated from their moorings and their anchors before they're actually out of battery. And while we do have a process to go and get the buoys back, so we're not losing expensive equipment, we're always trying to figure out, well, how did this happen? I mean, moorings can break for a lot of different reasons because the ocean, it can be a great place, but it can also be a very rough place. It's not uncommon, however, to find that sometimes the moorings break because of our little fish friends in the water, particularly some big fish friends. So what you're seeing here is a picture of a mooring that was in Kauai. We had the Kauai buoy drift a few years back. We went to get it, and then a little while later, we got on a boat of our local contact there, and we drove out to where we knew the anchor was and the rest of the mooring was, and we recovered it. And anytime we pulled up a piece that had those telltale like triangular bite marks that you can see both on that long section of the rubber cord and in that broken section, we took those pieces and we quickly shoved them into a cooler that we brought full of dry ice. And we sent it to the biology lab at the UH Manoa campus. And they were actually to take the DNA from those samples and confirm to us that, yeah, this mooring broke in this way because tiger sharks probably were trying to bite and have lunch on the fish that were surrounding your buoy and instead got a piece of your mooring. And we went, huh, shoot, okay, we'll have to work on how to prevent that later. And so we've tested lots of different materials in the water to make them more shark proof. But that was a cool example of, evidence that sharks interact with the physics instruments in our water. And I love showing this to young students, especially because it gets them like so excited and re-engaged if I feel like I'm losing their interest. So that's the first big wave tool that we have. The second wave measuring tool that we have at the PacIOOS lab is this guy. This is called a spotter buoy. It's, you'll notice, much smaller and much lighter than the wave buoy. In fact, it's about the same size, even a little lighter than the gyroscope that's inside the big wave rider buoy. But it measures all the same wave parameters: height, period, sea surface temperature, wave direction. The first difference is that the spotter buoy is significantly less expensive than the wave rider buoy. These, when you buy them from a company called SoFar, they start at about, I think, under $7,000, which may sound crazy until I turn around and tell you that these buoys will start at $60,000. And that's like the simplest version that they are. So much more economical to get one of these if you're on more of a budget. So I think that is, oh yeah, so the second, like I said, these are much lighter. These also measure waves a little differently than the wave rider buoys. These measure wave riders through accelerometer, basically. Will measure the distance that the buoy is compared to the sea level height. This is using a GPS. And I think that's part of why this is able to be a lot smaller and a lot more affordable for lots of people. And that's why these spotter buoys are the tools that PacIOOS chose to use when we were creating the Backyard Buoys project. And the idea of Backyard Buoys is that we wanted to make a system where the community could invest and volunteer to invest in as many of these buoys as they wanted and have a community-run, easily accessible way to measure waves around their communities. That can just be easily accessed online. And I also believe that link is on the resources page for us as well. So when I talk to young students, especially about the differences between these buoys and why can't all the buoys be the size of the spotter buoy, this is the analogy I like to give. When I was a kid, I loved to play on Google Earth, and I could see the big picture of the whole globe, and I could see a satellite image of the ocean, and you can get a sense, if you do that, of what the ocean looks like. You can probably predict that there are some big waves, maybe even some storm systems if you're a person that likes to track those. But if you are in Hawaii, for example, and you want to know, well, what is the ocean doing around Hawaii specifically? Like if I wanted to get data on that, or if I just wanted to know, like, okay, if there's a storm over there, how is it affecting the oceans around Hawaii specifically? You'd want to look at the Earth through a magnifying glass because you want to be able to zoom in, but still get a nice, accurate, and enhanced picture of what the data looks like around that area. And the wave buoys, the wave rider buoys, are the magnifying glass in this analogy. But if you wanted to go even farther, let's say like you're a fisherman and you want to fish at the exact same spot every day to get your catch, or you're a surfer and you want to know, what are the waves doing at my favorite spot on my favorite beach? You want to look through through not just a magnifying glass, you want to look through a microscope. You're just not trying to get a sense of the generic, weather that, when you get the weather report, that's what you're getting, the more magnifying glass view, but you want a microscopic view of a very specific point in the ocean that's near to shore. And that's what the spotter buoys are for. They're the microscope of the PacIOOS wave monitoring system. But if you wanted to do this in the classroom and you weren't necessarily, sure about, oh, I don't know if I can get my whole class to the ocean or a big enough body of water to do this, we have ways to help you guys do this at home. So we actually, I believe there's some video examples of this as well. PacIOOS, we bought a mini accelerometer from PocketLab, which you can connect to the PocketLab app and network. And what we did is we 3D printed a hollow mini buoy that I'm opening up and putting the accelerometer in. And when we put the accelerometer inside, the vertical motion of the buoy is related to sea surface elevation. So the accelerometer is determining the wave data the exact same way that the wave riders are doing in the ocean that I put out all around. And when we put the mini buoy in our wave tank and we start creating waves, either by pushing the water around or by creating wind waves, I think we use like a little mini blow dryer for computers. We can connect this to the app and the students can actually see what different types of waves look on a data plot. So this can be done. It doesn't have to be done with this kind of wave tank. I know that Hawaii teachers, if they want to rent this wave tank from PocketLab or Hawaii STEM Pre-Academy, they can do that. But if you don't have access to a wave tank like this, as long as you have a bucket that's big and deep enough to hold a little buoy like that and tape an accelerometer to it or put it inside, and as long as you have enough space that students can push the water around and make waves or blow in it and make different types of waves, they can experiment with, what does a big stormy wave look like on a wave plot? Or what does a simple wind wave look on a wave plot? Again, as long as you have access to a big enough bucket, this is something that you could do in your classroom so students can actually see what a wave looks like in the real world and what it would look like on a wave plot and how we connect those two.
This is great. So when the wave buoy shows the data of what's happening now, we also can put into the model to get the wave forecast. We know we are run out of the time, but basically after the observation, we can understand underlying the physics. And then we use the mathematical equations to represent this physics. And we can use the numerical method to solve the mathematical equation and build a numerical model. So that's why this little sketch shows how we put the STEM concept into the model building. That's why when we have weather forecast, we feed into the model, we can get the wave forecast.
Thank you so much. Oh. There you go.
Sorry, I was muted. Olivia and Ning, that was fantastic. There's a ton of questions. So let's do there's some really cool questions here. I'm going to combine two. So two together. Heather from Kansas City is asking, can the buoys be solar powered? And then also I saw Amanda from Houston asking, was that a solar panel on the small buoy that you showed Olivia?
Yes. So not all of the Wave Rider buoys are solar. That was a thing that came out in some of the newer models. And I will say, even though the lids of these buoys are only so big, and so they can only fit so big of solar panels on the top, so they don't completely replace the batteries in these big wave buoys, but they do help extend the battery life of them. So that is something that has been added later on. And so the newer models of the buoys, again, this lab has been putting out wave buoys since 99 for about 20 years. And so the newer models that we have do have solar panels. But yes, all this, oh my goodness, I am so sorry. I knocked down my computer. Is everyone...
No worries, you're there.
Apologize for that big bang. The SOFAR buoys all have solar panels on top. And yes, so hypothetically, this can extend the battery life, not indefinitely, but for a very long time.
You know, and I knew this. This is great. Lisa McFarland from New Zealand is asking for the 3D printed buoy template, like if it's on Thingiverse. That's available, right? I know you have it, the 3D file for that.
I know the resource, does have the file for like the 3D model if you wanted to download that and if you have access to a 3D printer, yes. I don't know, does PocketLab, like, I'm not sure if the link also has a link to just buy them pre-printed though.
We don't, that's a great idea. I'll tell you what we do for everybody online. We just use a plastic Ziploc bag. And
as long as it can hold an accelerometer, it works.
Yeah, you're not doing precision measurements like Olivia and Ning are doing, right? You're just trying to look at waves and measure them. And it works really well. Just put it in a tub or a sink, a tub of water and in a Ziploc bag, connect it, and you will see it's amazing. Actually, this is really, really good data. And what's cool is there's not a lot of ways, to teach waves. Like everybody uses Slinkies and stuff like this. There's another way to do it. Hey, there's a ton of questions here. Did you guys know by any chances, Maria Fitzgerald in New York, are there any wave resources for the Great Lakes area? I imagine there's got to be wave views in the Great Lakes, right?
Yes, we put some links at the resources page. So there is NDVC website, CDIP website. So you can check it out. We know we have a lot of buoys around US. So yeah.
Yeah, PacIOOS stands for Pacific Islands Ocean Observing System, but there's tons of different IOS programs all around the US. So we just handle the Pacific Islands buoys, but there's an Atlantic one, there's an Alaska one, there's one for the Great Lakes, and they don't all use the Wave Rider buoys, they don't all use the SOFAR SWAR buoys, they use all different types of stuff. So every lab is a little bit different depending on what they think makes sense for their body of water.
And I love this question. This is Abigail from New York. What's what are shark-proof materials? What's the most shark-proof material you've found?
Oh, do I have a sample? Hold on.
This is a great question, by the way. I love that.
Yes. Okay.
And I love the story that okay, so if you have material on it, you can go analyze the DNA and figure out what it was because you want to know, right?
Here you go. I have a box that is full of a very fancy line that's literally called Shark Bite Line, SHARKBYTE, which is meant to tell you what it's designed to prevent from happening, basically. So this is it's very brittle, and if I have to cut it up and slice it, it can be a little tough, but it's very buoyant and hollow in the middle, but it's also a very tough polyurethane compound that is designed to handle shark bites better than other forms of line that we have. And I'll use this in different sections, different parts of the mooring, depending on how deep I think it's going to be in the water column and how likely I think that that site is going to be bitten by sharks. Like, for example, I absolutely put this on the Kauai buoy and some others that I know there's a lot of shark activity, like the North Shore of Oahu. But not all of them. It really depends because, this could be more expensive than some other materials. And sometimes I'm more focused on, is the line more durable for different types of damage, depending on what I think is the most likely source of damage at each individual site.
I don't know if you guys are watching the chat, but Joanne said that's shark floss. I think that's pretty good, pretty clever.
Right? Yeah.
Hey, Ning, these are probably good questions for you. I'm gonna put a couple of them together. And this is from Foster Hayes from Ohio. So so matter is not carried by the waves. How does that relate to the movement of tides? So the waves. So let me read it. So if mass is not carried by the waves, how does that relate to the movement of tide where the mass of water is rising or lowering? That's really interesting.
Yes. So that's a great question. Tides is a different type of waves. It was controlled by suns and the moons. So for the ocean waves we see at the beach, the period is about 16, 18 seconds. But for tides, the period is like a day or half day. So with a longer period, the wavelength is much longer. So if you can see the movement of the water particle beneath the waves, and the water particle move in the circle, but the circle under the tidal wave is much bigger. So that's why you see a large back and a forth movement. So that's also because that's underneath the waves, the movement of the waters. But over time, on average, the same particle still remain in the same place. That's why.
I love that. That's like a trivia question. Like what wave has a 24-hour period? And you can say the tide, right?
Yes.
That's really great.
So,
oh, go ahead. Go ahead.
So that's why you see Alaska, the water temperature is much lower than Hawaii. So if it carry the water away from Alaska to Hawaii, a few days later we're going to have very cold water. But actually, our water remains almost the constant, the same warm temperature.
I love that. That's a way to explain that the matter doesn't move, the particles don't move, right? Oh man,
Yes.
that's so good. And there's a related question. This is from Christy Rinson in Manitoba. Well, okay, so what happens? Her question is, so then how does water move onto the beach? Like if the water molecules are not actually moving, what's happening at the beach?
You really ask a great question, because when waves go to beach, the water depths became shallower and shallower. Then the waves tend to break. As the wave breaks, then the particle move. That's why it can flood the beach. It can cause erosions. It can give a lot of problems. So the coastal wave interaction with the beach is a very complex research area. But your observation is great. Fantastic questions.
And boy, we're just at time. This is related to wave energy, right? Like harvesting wave energy in some ways.
Absolutely.
Yeah,
Yes, absolutely.
is that do you do that research, or is that kind of fed by what you're doing or parallel to what you're doing?
Yes and no. So those projects do happen, and we will sometimes provide buoys for other projects and labs and groups they'll say, hey, we want to see if we can capture waves at this specific site, but we'd like a buoy so that we know like what we're working with on any given day and how we can relate the live buoy data to what our generators are producing. So we work sort of in tandem with wave energy projects and labs.
Yes, and my another affiliation is the Hawaii Marine Energy Center. There is a group of researchers trying to find ways to harvest the wave energies to produce green energy.
Okay. Oh, that's fantastic. Hey, Ning and Olivia, we have to go. That was so interesting. I really love it. Yeah, you can see the audience loves it. Hey, thank you, everybody. We're going to take a little break, and we are going to come back, and we are going to talk to Okihi. And you're going to get a break from me. We're going to have an amazing guest interview, and that is Lauren Kopp from STEM Pre-Academy. And by the way, I saw some people put it in the chat here. If you are a Hawaii teacher, and if you don't know Lauren, you should. She has a lending library, I will call it, of amazing science equipment, including some PocketLabs in there. So you can get a wave tank from her, believe it or not. And you should reach out to Lauren. Make sure you know Lauren and reach out to Lauren, and she will give you some great kit for your science classes. Okay, so let's go to a break. Thank you again, Olivia and Olivia, and we'll Ning and Olivia. Oh my God. And we'll see everybody in about 10 minutes.